Welcome to this talk about temporal profile predictions for cell culture. My name is Christian Skytz. I work at Xavier Symphogen as an associate scientific director, doing data science primarily these days, but my background is in cell line generation and cell culture process developments. So here we have the presentation overview. We will go through the introduction, what is a cell culture process, and why is it relevant for us to predict cell culture graphs or profiles over time. Having the introduction in mind, we then proceed to model building, where we will, based on historical data, use FDE, Functional Data Explorer, and partial least squares to predict temporal profiles. Lastly, I will show you how to apply the models made on real-time data that is streamed from our scientific data management system. The intro part is myself and also Christine Møller Pedersen, who is a data scientist at Xavier Symphogen. The cell culture development process starts with a cell expansion step. That is where you take a vial with frozen cells, you thaw it, and then you expand the cells until you have enough cells to inoculate your bioreactor. In this case, the bioreactors are performed in fed batch mode. So basically you inoculate your bioreactor with a number of cells, and then over time you feed with different feeds and glucose while the volume increases. We are fortunate enough to have data from many different types of bioreactors. That would be AMBER 15, AMBER 250, shaker, and different pilot scale bioreactors up until JMP scale bioreactors. That would be 2000 liter. After the cell culture process, there's some downstream purification. There's a lot of antibody characterization happening. I will not go into that, but the end product is, in this case, an antibody drug that could be towards cancer treatment, for example. And this talk will be specifically about the bioreactor fed batch phase. Zooming in on the bioreactor fed batch phase, we have a lot of historical data at Symphogen. Many of these are typically DOE experiments, so there's a lot of variation in each of the experiments. And out of each experiment, we get many different types of relevant variables that we would like to assess on an ongoing basis, especially during the experiment, but also after the experiment, where we would like to compare between different systems, different scales. And since we are talking about many DOE experiments, we also want to know how parameters influence each of our graphs. So in this case, we want to talk primarily about live cell density, which is another word for viable cell density, and shorthand is VCD. And that is really how the cells grow over time. What is viable cell density? We have a machine. In this case, it's a Bicell Blue cell counter. A sample is applied on the system, and it takes around 300 images. Each of the images that you can see here is assessed by an algorithm on the cell counter, so that each of the green circles denote live cells, each of the red circles denote dead cells, and the aggregates cell agglomerations are simply discounted, and that are the red boxes. So this comprise one data point. So when you aggregate all of the different images, you get one data point out of it, and over time, when you string them together, you get a graph. A fed batch phase is typically 14 to 16 days. Why do we even want to predict each of these curves over time? By predicting VCD, you will be able to forecast how nutrients are depleted so as to be able to deliver glucose and feed in appropriate amounts to the cell culture. So if you deliver too little feed, the cells will probably die. If you deliver too much, there will be a lot of different stuff that can be impacted. That could be CQAs, inhibitory byproduct buildup, and many different things. Also, we will be able to predict peak biomass, which is relevant for clarification and harvest. We will be able to predict cell-specific productivity, which helps us predict end titer. And in the end, we are sure we are able to predict many CQAs from not only VCD temporal curves, but many others together. We have this tier-based approach. In the first phase, we want to build a process for predicting any type of cell culture curve, exemplified by the VCD curve, independent on parameters, even though we're doing a lot of DOE studies, and wholly based on historical data. That is what we're talking about today. Going further, we would like to incorporate all of our process settings, system types, to be able to process simulates. That is not now, but we are working on it. So how did we get all of this data necessary for building our models? We have a scientific data management system in-house here at Symphogen that is called MIMA. And MIMA helps us collect all of this data from the many data sources that we have in our laboratories across scientific areas. Data collected is transformed, cleaned, enriched with metadata and parameters, and then we validate each of the experimental data sets. All of this is saved in a database where we can filter and wrangle it into one cohesive, structured data set with metadata and parameters attached. And that is what we have done for all of these bioreactor experiments. So the data set that we are using is over 1,000 bioreactor runs. And with that, let's go for model building.
Take over here. So my name is Per Vase, and I come from Novo Nordisk Engineering, where I work in the manufacturing intelligence department. And I've worked plus 20 years helping clients to get more value out of the data, typically using JMP. Actually, I started with version 5, and of course, one of these clients are Christian. So the example we will show today is how we have helped Christian hopefully to get value out of data. And I will first overall describe the concept we are using, and then later my colleague Thomas will show how it actually works in JMP. So first some few slides, and then the interesting part in JMP. So what you see here are 3 typical VCD curves developing over time. And in this example, we are at the time point 6. So the full line is what we know until now, and the dotted line is what we're trying to predict. And you can see it's not just a matter of scaling, because the curve that is highest on day 6 is not the same as the curve is highest on day 10. So we actually need to be able to predict more than, it's not just a matter of scaling, it's also to be able to predict how they develop over time, because that can clearly be different. Yes, so if we go into the next slide. And the overall concept is that we use historical data to define what is normal here, and we use the functional data explorer. So we actually establish a mean curve and a shape functions, which are common for all the historical curves we have. And then, of course, we get individual functional principal components, which you have to multiply to the shape functions. And then when you add up with the mean curve, you get the sort of the final curve. This is how we describe the historical data set we would like to build a model on. And because spread clearly increases with level, we actually do it on log VCD, because we cannot do weighted regression in the functional data explorer, but we can take a log and response, and that gives you to some degree the same. Then when we have the FPCs and we have our PLS models, between how FPCs depends on the VCDs we have seen until now, we can predict the FPC scores, and thereby we can predict the complete curve at any given time point. And now I will dig a little bit deeper with each step. So we have divided into 6 steps. First, we are filtering the data, meaning taking curves out we might not want to build models on for different reasons. I'll go back to why. Then our PLS model requires that observations are at equidistant time points, which they are typically not. So we need to fit all curves with, we do a cell growth model, and then we can interpolate to the same time so they get equidistant. And when we have this, we can make the functional data explorer, so describe each curve with some functional principal components, which are individual for each curve, and some common mean function and shape functions. And then we can model these FPCs with PLS, so we can actually predict how a FPC is going to be based on the time information we have until now, and thereby predict the rest of the curve. That's what we do on historical data. And now we want to apply these models. So when we have a new curve in production that rolls in, we have data at a given time t, let's say time 5, then we have 6 time points, because we have times 1, 0, 1, 2, 3, 4, and 5. And based on this, we can predict the FPCs from the model we have on historical data. And from the model on historical data, we also have the mean functions, we also have the shape functions. And by adding all of this up, we can actually predict the full curve. That's basically how it works. And I think I'll go even deeper with each step. So look at filtering the data. Here you can see a lot of curves at a time, and you can see they look very different. So we can not just assume everything is like the mean. That would be crazy bad. And you can also see that some of the curves, well, it may be hard to see in this figure, but there are some of them who has very few measurements, because not all the curves you have many timely measure points. We take these one out because they are hard to model. There are also some curves where there have been deviations. We don't want to use these either because something went wrong. This should not be normal. And there are also some extreme curves that might sort of skew our model because they will have a too high influence on it. They are also taken out, but we still want to predict them, and we will see that later on. So first we clean out the curves and only keep the ones we would like to build models on. So that's step number 1. Then step number 2, the input for the PLS is what is the value at time 0, 1, 2, 3, 4, 5, and 6. And because they're not all measured at exactly the same time points, and some time points are missing, we actually need to first interpolate the curves. So, and of course it's cell growth. So obviously they can be fitted with a 4P cell growth model with a Y max. That's how high you would have been if you didn't have mortality. Y0 simply where it starts, division, the early exponential growth, and the mortality, the rate they die over time. And by fitting with these 4 parameters, we can get a nice fit to a VCD curve, obviously because it's a cell growth model. And then we can use this model to interpolate data, so we get all curves at exactly the same time points, and at the same time, we can actually also remove noise. So basically, in the step 2, we remove noise, we make them equidistant. And then we are ready for step 3, where we now can go in to the functional data explorer in JMP, and we can then find across all our historical curves some common mean functions and some common shape functions. And the way curves differ will then be what we multiply on the shape functions, what is called functional principal components. So each curve is described with the same mean function, with the same shape functions, with different functional principal components. And by adding this up, we can actually describe the full curve. And when we have all of these functional principal components, we can at each time point try to predict all the FPCs. Typically we use 4, and we have 17 time points, so we actually end up with 68 models, because one model for each FPC at each time point. And we use PLS because, of course, the time points are heavily correlated. VCD at time point 1 is closely related to VCD at time point 2, and so on. So PLS works fine here. But the functional principal components are by nature uncorrelated. That's why we model them one at a time and not together. And that actually adds up with 68 models, but by scripting, it's not really a big issue. So we fit a lot of PLS models. And this is how it looks in JMP. You just go into fit model and say that your response is the functional principal component, either 1, 2, 3, or 4. And then you simply add in all the timely measurements we have until now, including interactions and curvatures, so actually a response surface model. And based on this model at each time point, we can then predict what is the FBC going to be. And here you can see the same equation again. So we predict the 4 FBCs at a time point k based on the log VCD we have seen until this time point will be at time 0, 1, 2, 3, 4, up to k. And then we can predict, have a model for what is the functional pillar component, depends on what we have seen until now. And then we can actually predict the full curve based on the shape functions, the mean function, and each principal component. That's sort of how we predict in the production how it's going to work. And here's an example on how it works. There are just 2 typical curves, and the dots are actually measurements. You can actually see the noise here. You can also see the missing points on the wet curve. We don't have the late part of it, so that's why we need to make this equidistant curves and take some noise out of it. And you can see on the left, you can see it at time 1. So we only have 2 time points, 0 and 1. And actually the blue one can be fairly well predicted. The wet one is clearly predicted too low. If we go to time point 5, it's more or less the same. Of course, the prediction on the blue curve still works, but the prediction on the wet curves has maybe become slightly better, but not much better. But when we go to time point 8, of course, now we can clearly see that the curve is better. The prediction is better at time 8 because now it's very clear that it goes faster than the blue one, which is hard to see before time 5 and earlier. And of course, remember that we might not actually need to predict the rest of the curve because for concerning nutrients, we actually just have to predict until the next feeding time, which is typically 2 days ahead, because at that time we will typically measure VCD again. If we try to evaluate the general performance of these, so to have a kind of a metric, how good is it? Then we can see the same example in the upper right corner, where the dotted are the actual observations, and the black curve is the curve we can fit when we see all the observations, and we call that sort of the true curve. Then the green curve is the fit we can make based on observations up to day 5, and of course this is not the same as the true one, it's a little bit lower. And the wet curve is actually the prediction you would make if you thought all curves were the same. It's basically our mean curve from the data explorer. And then we have as a metric we integrate from now to day 16 is where we typically end these ones. And then we say the integral of the black curve is actually the true one. And then the integral of the green one are the predicted one. And the integral of the wet one is actually the one we would have used if we had no model, just assuming the mean is the same every time. And what you see in the graph in the lower right corner is actually the relative integral difference of the rest of the curve as a function of time on the x-axis if we do it at time 1, 0 up to 16. Of course, there's no value at 16 because we use the curve at 16 as the reference. But you can see in the beginning, we have an error rate around 18% because it's hard to predict just on the first one. And then gradually it becomes better and better. And already at day 5, which is the typically first feeding time, it's down to 12. And then at the end, we are down to around 3%. So it gives a fairly good prediction of the integral of the rest of the curve. The red bars is the prediction error you would have made if you just use average. So we can see the difference between the red and the green. It's actually what do we win by having in this model concerning the ability to predict the integral of the rest of the curve. And but remember that, as I said earlier, if you're only talking about feeding, actually we only need to predict the next 2 points. And of course, then prediction errors will be somewhat smaller than I showed on the previous slide. So then it will work even better. But we actually just find it's a good metric, our ability to predict the rest of the curves. And of course, it's very important to have the right prediction for the amount itself, because the consumption of glucose, for example, is proportional to number of cell days. At least that's what we assume. And then, of course, the feed demand depends on the consumption, which is basically just the integral of the curve 2 days ahead if you feed every second day. And what you can do here, make sure your cells don't run short on nutrients if they go faster than they normally do, or in the case where they go slower than they normally do, you can prevent excess feed, which of course is expensive and can even be harmful to the cells. So just before I switch over to Thomas, with John, I would say, of course, doing this work, we have been inspired that something could be done better and actually at the same time simpler. So right now we're actually working on a concept where instead of having these 17 type 4 PSL model, actually just make one PCA model that also describes the variability in the FBCs, and based on that we can sort of penalize unnormal combinations. And also we're working on that these 1,000 curves we are using here, we know some systematic differences between them. They come from different type of bioreactors. They have used different recipes, and clearly we can see that the reactor type and the recipe sort of change the shape of the curves. And by that, we can sort of have different starting points of the fit, and we can put that into a loss function. Because if you go to, and we can also actually replace the FDE with a 4P cell growth or an asymmetric Gauss, which is better and simpler. And there, if you go to a nonlinear platform, it's pretty easy to put in a loss function that penalizes not just the sum of squares, but also if sort of is this combination of model parameters expected based on the type of bioreactor we have used and the recipe and so on. And going to the nonlinear platform, we can actually also put in a loss function that can handle weighted regression. So we can do a much more proper transformation than just a log. We can actually make a log variance model and penalize with that one. And we can clearly see that gives better results. But now over to Thomas, who will show how this is done in JMP.
Yes. So my name is Thomas. I am also from NNE. I work in the same department as Per. I'm a data scientist. And today I'm in charge of showing you how all of this looks in JMP. I made a workflow. It's a smaller data set. It's just to give you an example, run you through the same steps that we just described, but sometimes it's easier to describe in practice. So here we have the data set where we have 4 columns. This is the raw data, let's say. ID corresponds to a specific curve. So we have these measurements for the first curve. These are the times at which they were measured. The unit is days. So at day 0.06, 0.84, 1.78, they were measured. And the planned day is where you should have actually measured if you had a perfect timing, right? And here we have the VCD per milliliter in millions. You can see some of the data are missing, and that's what Per was talking about. Sometimes there is just missing data or not measuring at the correct times. So we will have to take that into account. Anyway, the first step when looking at data is always nice to just make a graph and see what is in here. Here we have all of the curves over time, all of the measurements over time. And you can see there's different shapes in the curves. Some are low, some are high, some peak early, some peak later. And at the end of the day, what we want to do is capture this variation, understand the shapes, and kind of predict future curves based on the first measurements. So here I'm showing all the curves. But what I can show you now is if we make 3 different groups. I named them the good curves, the ones we keep. But in the data filtering step, we want to remove some of them. For instance, there are some curves where you just measured 1, 2, 3, 4, 5, 6 measurements instead of 16. And these can be a bit hard to model and incomplete. So we don't want them in our main data set where we want quality data, so to speak, because it's historical data, right? There are some curves that don't really decrease, and this can give some problem later on. So we just also choose to remove them from our original dataset. So we end up with a set of good curves. Also, something worth noticing is that at the beginning points, the spread between the points is kind of low, but the more you move through time, the bigger the spread. And this is going to be a very important thing to consider when doing the modeling. Anyway, we just save the plot and close it. Next thing we need to do was the pre-processing of the data. And actually, before I open that up, I'm going to show you that I have two hidden columns here already put. In JMP, you can make formulas, but also you can put certain equations if you put some parameters. So this is the cell growth equation, 4-parameter cell growth equation that Per was showing in the slides. So basically what you're saying is you can describe any of those curves through 4 specific numbers: Y max, Y0, division, and mortality. And of course, you pick a specific day to evaluate the formula at. Also, we have a loss function that we're going to use it in the model, because if we don't put a loss function, if we just optimize based on the curves, this variation that I was talking about in the middle, it's going to completely dominate the algorithm for JMP to find the optimal curve. So just for now, remember that we're not using just the sum of squares to optimize, but we're using a loss function. And I think it's clear if we open up the nonlinear platform, where in JMP you can say, I want to model all my curves, so find the optimal parameters per ID. And if we click run, it is going to optimize and find the best fit curve across all the curves. You can see it's fairly well fit. And it's going to take into account that there's more noise in the middle than at the start or at different time points, because we set in a loss function. If you want more details, then you can, of course, ask more about it. But for now, just keep that in mind. Anyway, once we have fit all of the curves that JMP gives us, then we save them into the dataset. You can do that just right-clicking and save formula. And JMP will give us a new column where for every specific curve, you have saved the parameters corresponding to the curve, and then you have just literally the equation from the model. So now we know what the model thinks. So now we're in the curve, not at the specific points, but we still have the problem that we are evaluating at the actual day. And we kind of want to move them all at the same time. So we need to substitute into planned day at the time where we want to look at the measurements. So you can see now we have planned day. You can do that very easily. And now, because we're going to use the FDE, one of the assumptions, again, when using FDE is a constant variance across time. So we take a log to deal with that. The next step is to open up the functional data explorer. And actually, you can find it here in specialized modeling. And I'm just going to show you real quick that if you put your ID, your normal VCD, and you were to model it without the log, then you can see the variance is not the same throughout the levels, and that is a problem. So that's why we take the log, and you can see we have sort of even error across time. Anyway, we have the functional data, and for those of you who are not really familiar with this platform, what you do here is you take data that is across time, so not just only one measurement, but now we're dealing with a function. This all relates to one specific curve, and make some models out of it. Here we can see we have a mean function. How does it look in general? And we can see the standard deviation across time. You can see it's still a little bit different. Then we can always fit a model. In this case, we fit with B-splines. And now for every curve, we have fit a function. So this is an alternative to, for example, the cell growth model. This is just a different way to model the curves. And it also does some functional PCA. It's like PCA, but in functions. And the way this works is you calculate a typical curve or log curve, And then you describe all of your curves with 4 different main functions and a specific weight attached to each function. It is easier to see down here. We have a profiler where we say this is how the curve looks, but how much do we have of the first principal component, the second principal component, third principal component? If we change how much we have of a specific one, you can see we get different shapes and different levels. So how much you have of each shape function determines how your curve looks. And once we have done this analysis, we save the summaries. Now we have historical data, so we have the FPC scores for each one. And we have as well the shape functions here. We want it in one data table, so we have it saved in the original data table. That's what we're doing here. Then I'm going to do a little bit of pre-processing before doing the PLS models. This is something I need to do because it's of course very nice to work with the tables, click and point functionality, but sometimes we do need either data stacked or we need it split, so in different formats. So what I'm doing here is simply saying our log cell growth model that we had at the start, we want it at every time point. We only want those observations for now, because we're going to fit PLS models for each time point. So for instance, when we fit the PLS model for time point 4, we only need information up until time point 4. So we need to delete the rest of the data and just calculate based on that. It is almost done. So we have 16 time points. It is calculating that. And there we go. Now we need to split the table. We need it facing another way. You can see now it's in the split format, but those are just details, so we can actually do the PLS modeling. And now I have clicked the loop because it takes a little bit of time, but you can see the functions that we're calculating and saving are the PLS models that Per was talking about. So here we have, for instance, PLS model for the first FPC at time point 0. PLS model for the FPC at time point 0. For the second, third, fourth FPCs, and then at the first time point, at the second time point. And we're going to end up with 68 different models. Just as a reminder, we are using PLS because it deals well with the correlation, because it's time data. So of course it's going to be correlated. If a previous time point was high, you expect the next one to be also kind of high. But we are modeling each FPC individually, because if we were to model them all together, then the model would try to compensate for the errors on all of the FPCs equally. But of course, we know that the first FPC drives or explains more of the variation in the data. So we kind of say that is more important. And then the second one is also next most important, and so on. So it's almost done once again. So now we have all of the PLS models saved in here. So I think because of time, I will go to show you the output of such models, because this is something very interesting. So what I'm showing you now here are 2 curves and some points. The points are the raw data. The red curve is the initial model, the cell growth model that we think we have with all of the data. And the blue line corresponds to our prediction at a specific time. In this case, it's the first curve, it's one of the curves, at time point 0. So we have only seen this point, and our model says we think it looks like the blue curve. Of course, you cannot expect it to be so precise with only one measurement. How are you going to know? But if we go through time, so we have one more measurement. So now we have these 2. So now our model says, I think it looks like this. And if we go down through time, it adjusts on what it sees. and eventually it makes a very good predictions. But for this example, you can see already at time 5, 6, you have a pretty good idea of how this curve looks. And you have this for any of the curves that you see here. And of course, if you get one new curve, you can also predict that for the new curve. That's the main idea here. We're actually predicting at any time point how the curve looks. And even at time point 5, 6, we're already getting some really good fits. Well, this one may need a little bit more time, right? But you get the point. We save and close that plot. And this is just an extra just to show, similar to what Per showed in his slides, is that we can also calculate the integrals and the errors made from the integrals. I'm going to show you in a plot. So if we had only used the mean curve as a reference to model the curves, then we're getting in this data set, of course it's a smaller data set and different curves, a 15% average error rate, relative error rate on the difference between the integral that is the truth, so to speak, and our predicted. But if we use our method, you can see already after time 5, we're down to 5-6% relative error rate to the true value. So this is where the method shines, in that we are able to predict from kind of early on the rest of the curve fairly good. And that means we can also predict how much we should feed them. And that, of course, means we get ultimately, we put nutrients where they need to be, and we don't take them away where they shouldn't be. That's kind of what we're doing. So that is my deal. So I think it's back to Christian now.
Yes. And here we go. Okay, so all of the stuff that we just saw is, of course, incredibly complex, and every user in the world will really want to ignore that. So how do we make sure that we have to go down here? How do we make sure that the user doesn't see it but gets all of the benefits? So we have this is a completely different project, but we have made a JMP add-in that imports data from our MIMA scientific data management system. And the cool thing about this add-in is that you can build in any type of routine analysis atop of whatever data that you're importing, because each of the data sources are structured and the same every time. So in this case, we have a barcode from for our workflow, which is a data set on MIMA that we can import directly from the database using JMP. It will then present all of the different data sources available for that particular workflow. We select the Bicycle Blue, which is a cell counter. And then the data set will be imported. It doesn't take too long. And as you can see, routine analyses are accessible via scripts directly in the JMP data table that has been imported from MIMA. And that is something that I will show you now directly in JMP. So here we have the imported dataset. There's metadata and parameters that are virtually joined to each of the tables. This is the table you directly import from MIMA, a cell counter table. And this graph builder shows for a particular bioreactor that we are currently on day 9. And we would like to predict the rest of the trajectory for this particular graph. And this experiment is also a DOE experiment, and it's an AMPER-15 experiment for those of you who know what that is. It's a microbioreactor system handled by a robot. So this script down here is the application of the models. And I don't want to press it right now, I have done it already, and this is the table that comes out of it. Without diving into too many details here, I will go directly to the graph builder for this table. And here we can see for the same bioreactor I showed just before, on day 9, we have models applied on the data points for day 0, when we only have this data point down here, day 1, day 2, and so on, up until the most recent prediction, that is day 9. So we see a pretty close curve compared to with the real data, and then we get a pretty good idea on the trajectory of the remaining portion of the experiments. And again, we can filter on few or many bioreactors, and also to that apply models that Thomas has shown you for us to be able to deliver feed in proportion to what the cells need. And that is what the user sees. And then we are at the end of this talk. So using around 1,000 structured contextualized bioreactor runs, we were able to build models that right now are being applied to real-time data that is being streamed up into our database, where we are able to import it directly to JMP and apply these models. So this is the first phase, and the next phase for us is definitely going to be something where we want to explore process simulation, where we put on all of our DOE bioreactor set points and scales, systems, and any type of metadata and parameters that we would like to look at. So with that, thank you very much for listening.